All right, so we got another joke to read. It's a little one. Oh, I got chocolate on it. It says, what do you call a train carrying bubble gum? It's not over yet. It's called the Choo-Choo Train. All right, let's cheers. Let's eat these cookies that we made earlier today. Cheers. Cheers. Nora, do you know what those little diagrams are?
No.
They're water molecules. Can you make some lines between them all? Good. Now connect them together. Connect them all together. All together. The top ones too. Don't forget to put lines through the top ones. Okay. Just make sure that green one gets connected. Okay. Now can you connect all those lines you just drew together? Just draw a line down straight through all of them. Yes. Now keep doing that going across. Perfect. Okay. Now I'm going to swing this around. So Nora just made some bonds between water molecules. Now every time she made one of them bonds, energy was released. Energy was released because whenever you make a bond, energy is given off. So
I need to do that.
So yes, I'll show you in a second. So all those red lines are little forces between every water molecule. And if we make them, that gives us energy. But if we gotta break them, they're gonna take energy. Okay, now this energy is called enthalpy. Enthalpy is the energy that's all in that particular pile of molecules up here. But that's hard to measure. You can't measure enthalpy. It's unmeasurable. What we can do though is get this whole thing up here to go through a change.
Do I need to draw it?
Watch, I'll show you now. Go through a change like melting, and what we can do then is get it to undergo an enthalpy change. So that's very measurable. And our little experiment is going to get us to do an enthalpy change.
Do I need to draw it?
Determination. No, we don't need to draw it. You got your drawings already made. So all those lines again are bonds. Bonds that when they're made
Do I need to
give
do
off heat.
this?
So when ice is created, heat is released. But of course, to break ice down, it needs to take heat. Without heat, it will stay as ice. And hopefully, we can get enough heat to get rid of all that ice outside. Okay, so we're going to talk about the first law of thermodynamics. Okay? Yeah, it rubs off. And all it says is that the heat that's in any system is the heat that goes into any surroundings. Okay? So, in our ice cube melting experiment, the heat that was in the water went into the system, the ice, and broke down the system. Okay? Now, there's no temperature change, Nora, in our system when it melts. Okay? There's no change in temperature. So we have to use this formula right here. What's your hand? And this formula is called the enthalpy formula. Now, let's point out all these things here. That's heat. What's next? Mass, M, specific heat capacity, change in temperature, and moles. Okay, that's all the symbols we need. So, everyone knows that does this, that the system's heat is what goes into the surroundings, or opposite. So we can put these all symbols together to stand in for our heat, okay? So my 3202 students are used to this. Don't touch it yet, but they're not used to this. This is a new formula, but the same thing. That's heat. So what we're going to do in our experiment is solve for what's called the enthalpy of fusion, okay? And that's symbolized by a delta H, which is really the same as heat. It's really the same as heat, but it's done per mole, not by MC delta T. It's done by the mole. Anyway, that's what our experiment will do. Yes.
Let's see you.
Okay. All right, so it's started now. We're gonna get Mom to edit out this first bit, okay? Get this bowl off. Clear that out. Okay. All right, hello everyone. We're gonna do our fusion experiment. This is an enthalpy experiment.
Yes.
We're gonna see how much energy ice takes to melt. Nora's gonna do it too, and we're gonna average our results. How's that sound, Nora?
Good.
Okay, so we're gonna need 100 grams of water first in our cups each. So I'm gonna use this graduated cylinder and room temperature water. Okay, I'm gonna pour it in your cup for you, Nora.
Yes, please.
Perfect. I'll do the same in mine. Okay.
Just something on the cup.
Yeah, so 100 milliliters is 100 grams of water. That's important to know. Now, what we got to do now is get our thermometers in our cups. So you can put your thermometer in your cup gently, and I'm going to put mine in mine gently. There. Now let's face the numbers. You can see yours, and I can see mine. Okay. Now, Nora, so we got our mass recorded, and I got my mass recorded, 100 grams. Now we got to get an ice cube. Okay.
Ice cube.
Fresh from the freezer. Put your bowl up here. Let's get this turned on first. Hold on, you gotta turn it on first. All those numbers gotta go to 10. Okay, now it's ready. Now you can put your bowl on. Do you want the small ice cube or the big one?
I want to get mine.
Okay, I'm going to use this one, okay? Let me clear it out. Okay, this is my ice cube. It weighs 11.52 grams. 11.52. I'm going to write it down.
Matter.
And my temperature right now is 21.3. 21.3 degrees Celsius. Okay. And now I gotta put my ice cube in the water. And now you get one here. Which one are you using? I gotta help you knock it out first.
I gotta get a grip.
That one's a good one.
It's slippery.
It's slippery and cold. Okay, what's yours say? 10.36. 10.36. Okay. And you were at 21.3 also. 21.3 degrees Celsius. Okay. Now we stir and we wait. Let's stir very gently with our thermometers. Gently. Okay. Okay. All right. How's it looking?
Good.
Almost gone?
Yes.
Okay, mine too. Okay, we'll keep stirring until it's all gone. Okay. What's your temperature at? Mine is at 12 or something. See what yours is at. Okay, yours is at 13. Hold it up here. Look on this plastic thing. Hold that plastic ring. Yeah. Hold it higher, yes. That way you don't warm up the thermometer either. We don't want to warm up the thermometer. My ice is almost gone.
Mine too. I gotta do a bit more.
Me too, a little bit more. So it didn't take too long. I'm gonna have a drink of coffee.
Mine's gone.
Yours is gone? Okay, so what's your temperature? Your final temperature is 12 degrees on the nose. 12 degrees on the nose. 12.0 we'll call that. And mine too. Mine is gone now too. And my final temperature is 11 degrees. I must have had a slightly bigger one. 11 degrees right on the nose. Okay. Good job on the results. Okay.
What else else we need to do?
Okay, Mom's gonna. So I'm gonna get my number of moles of my ice first, because we can't work with that formula. So here's the moles: 11.52, 18.02 molar mass gives us 0.6393 moles. Let's do Nora's moles. 10.36 divided by 18.02 gives us 0.5749 moles. Okay, see, I knew mine was slightly bigger than yours.
Mine was good.
Okay, so now I just gotta write all this here, and then I'll show you the answer. Okay, so I left you without the calculation done. Now all the numbers are in place. Your mass, specific heat capacity of water, which is known. And there's our delta T. That was my delta T. I lost 10.3 degrees Celsius in my water. So that's where all my heat came from, my water itself. Nora lost only negative 9.3 degrees Celsius. So she lost less heat in her water, mainly because her ice cube was smaller than mine. So in the end, after we put that and along with our temperature change and our moles together in a calculation, we get 6.741 kilojoules per mole and 6.768 kilojoules per mole as our enthalpy values of melting ice, fusion of ice. That's the accepted value right here in the world, 6.02. So we're pretty good. 11.9 for me, 12.4 for Nora. For her first ever experiment, that's excellent, Nora. Excellent.
No. No, this is for me. You're too bad. Out. Out. What is that? Can I stir it up? I'll stir it up. I want to stir it up too. Let's stir it up too.
Here, you can use my fork.
Okay. I want to do what? I want to use a big one. I want to use a big one. I want to use a big one. No, me. So.
Beauty.